I wanted to make one more short video showing how a building controller, a DDC or direct digital control system such as this, the Distech Model ECP410, could be used to control something as fast as a motor speed process. Here we have a small DC motor generator set which we're using out of the process, and the ECP controller right here is being used to control the speed of that motor. The reason this is so ugly here, all these patched in jumpered wires, that normally this motor is controlled by the Siemens controller, and we have everything all neatly wired together, but I had to take that apart and patch in wires temporarily so that this DDC building controller could be used for the purpose. I took another video showing how poorly this controller was working on this particular process, and I was using that to demonstrate a point that the scan time of the DDC controller was so slow compared to the response time of the motor. It was just a very poor match. And so with normal proportional or integral derivative type tuning, it just wasn't working very good at all. What I've done here is I've made a control much better. As you can see and hear, the motor's maintaining a much more steady speed. And the way I was able to achieve that is by radically changing the tuning of the controller. Given the slow scan time of the controller, that effectively added a large dead time to the process. When I say large, I mean a large dead time in relation to the actual response time of the process. Here in the PID control block, if I zoom into this, you can see the tuning parameters. And what I did here is I basically turned the proportional action off by setting the proportional band to its highest possible value. I also turned the derivative off by setting it to 0. This implements the parallel PID algorithm, which means I can essentially turn the gain of the controller off and still have strong integral action, which is what I've done here. I've used integral action instead of proportional to control this particular process. It seems to handle the dead time much better. With a fairly large gain, what happens is that dead time introduces a phase shift, causing it to very easily oscillate. Here, I've turned the gain way down. I'm using strictly integral action to control the speed of the motor and no derivative action whatsoever. That would be very bad on a system like this with a large dead time of the controller. So what I've done here is I've got a place where I can enter a set point. Right now the set point is 60% motor speed. I'll increase that to 70% motor speed, and we'll see how the motor responds. Coming over here, you can hear the motor speed change. It went up a bit, went back down, hunted just a little bit, and settled in at some new speed, which is much better performance than what we had before when I was running a more customary PID tuning set. I will change this set point again from 70% down to a lower value. I'll go to 50%. And we can see right here, some numbers change. We're at a PV of 70 right now, down to 53, 38, 37, 37, 46, 55, 57, 53, 53, 50, 48, 49, and it's settling in there at 50% motor speed. I can magnify this a bit, get a better view of it, and show you the performance again. Here we go. Magnified view. And we see the motor feedback, the motor speed right there, 50%. I'll change the set point. Let's go up to 80% here. We'll watch the motor speed hunt around a bit as the controller struggles to find its new set point. 73, 74, 78, 84, 85, 80. Actually, it settled in rather nicely there. If I decrease the set point, let's say down to 40%, take a big step down, we'll see how it responds. 80, 48, 48, 44, 38, 36, 37, 35, 38, 43, 44, 43, 40. So it took a little while to settle in, but it's actually doing quite nicely. Far better than it was doing before when we had fairly strong proportional action. And again, by the motor, you can occasionally hear the motor change speed. The update speed of the DDC control is still fairly slow, so it takes a fraction of a second between updates. You can hear the motor occasionally change speed. If I load it down with my finger, of course the controller senses that. Integral action winds up and applies more power to the motor control drive circuit. Now when I release my finger from the shaft, it will overspeed, but then you can hear it correct. So it's actually doing an admirable job of controlling this very fast process. despite the fact that the DDC controller has a very slow update time. So you can see how proper tuning can help overcome certain problems. It's certainly not a complete fix, but we can get decent control out of this system, far better than we had before, just using the right tuning.